is done as of now. Now we go to the second part, which is called the lexical selection. The goal of lexical selection is to choose an adequate translation in the target language from among several possible translations for a given source language lexical unit. An FST based module that allows the writing of rules has been in use for some time. Apart from manually written rules, a system has also been developed that learns through a maximum entropy model trained in an unsupervised manner. Okay, this is a deep learning thing. The training method requires only a source language corpus, a statistical target language model, and the rule-based machine translation system itself. All possible translations are scored against the TL language target language model, and these scores are normally normalized to provide fractional counts to train source language maximum entropy lexical selection models. Structural transfer handles differences between the source and target languages in terms of word order and morphological information by applying transfer rules. In the chunker model, these transfer rules function by matching a source language pattern of lexical items, creating chunks, and applying sequences of actions to convert the word order and morphological properties of the chunk as per the target language. There can, however, be more than one potential sequence of actions for each source language pattern, as well as overlapping patterns. To generate an accurate translation, transfer rules are applied in the input using a left-right longest match algorithm. Work has been done to extract or learn chunking rules using alignment templates. A parallel corpus is searched for sequence of lexical units that exhibit differences in order or morphological information. In addition, chunker rules can now be weighed so as to apply different rules in different overlapping lexical environment. These weights can be learned using an unsupervised maximum entropy approach. The basic goal of this method is to choose between conflicting structural transfer rules based on the lexical environment. For example, the Spanish sentence encontre two different translations to English depending on the syntactic parts in Spanish. This is detail specific here. These parses correspond to different sets of transfer rules, each of which could be matched. A single verb phrase consisting of verb, determiner, noun, adjective, or B, a verb followed by a noun phrase, determiner, noun, adjective, adverb, adjective. The noun phrase rule could specify that the elements be output in a different order. Determiner, adjective is a determiner, adverb, adjective, noun, and both rules that match the verb would add a lexical unit for the pronominal subject. Okay, so how we are setting the transfer rules is we have already tagged words with their type, like we have tagged word with verbs or tagged word with determiner. The word is noun, or the word is an adverb, or the word is an adjective. Now what we are doing is, while setting the rules, we are saying as if verb followed by determiner followed by noun followed by adverb followed by adjective. So this will always make sense. This is the essence of the transfer rules. we are setting the rule that determine a noun, adverb, adjective. So this is how the sentence will form. Okay, that was interesting. So now what they are doing, the noun phrase rule, let's go over it again. The noun phrase rule would specify that the elements be output in a different order: determiner, adverb, adjective, noun, and both rules that match the verb would add a lexical unit for the pronominal subject. A model is produced by running the source language text through all possible transfer rules. Okay, comparing the potential translations that are output through a target language model and dividing the scores by the series of source language lemmas that match each transfer rule pattern for a given potential translation. If the example above were part of the training data, then the potential translation "I found the cake very good" would score higher than "I found the very good cake" against an English language model due to having higher probability. This was very interesting. These different scores are then distributed as weights. Okay, it's a really genius solution actually. These different scores are then distributed as weights along with the input lemmas attached to the rules that each translation is the result of. These different scores are then distributed as weights along with the input lemmas attached to the rules that each translation is the result of. Okay. In this example, the weight assigned to the V det noun, adverb, adjective rule for the Spanish lemma is higher than the sum of the weights assigned to the V and verb and determiner, noun, adverb, adjective rule for these same lemmas, and hence the verb, determiner, noun, adverb, adjective rule will be selected. So this is how we are finalizing on the transfer rule. During translation, when a string of source language text matches multiple transfer rules, the system is able to choose between them, infer the correct one based on the weights associated with the rules that the source language lemma trigger. For example, if this same sentence were being translated, the verb, determiner, noun, adverb, adjective rule would be matched, resulting in the output "I found the cake very good." A contrasting example would match the same two sets of rules but would result in translation occurring through the other rule set. This is because the lemmas of the potential translation "I found a very good cake" would result in a higher combined weight for the V and det noun, adverb, adjective rules than the verb, det noun, adverb, adjective rule. This reason for this is that translations containing these lemmas would have scored higher against an English language model than translations like "I find a cake very good", resulting in higher weights for this set of Spanish lemmas attached to this set of rules. In both examples of Spanish inputs, using this approach and a suitable corpus to train an English language model, the set of transfer rules that result in the more likely English translation is chosen. This method has been tested using the Kazakh, Turkish, and Spanish-English translation pair, and it has been observed that the results are better when there is a greater number of ambiguous rules. The module has not yet been included in any released translation system. Okay, so we can try this one. New modules. New modules. Several previously unpublished modules are now available at the Apertium pipeline. discussed in this section are apophthegm recursive, which provides for true recursive transfers, apophthegm separable, which enables the processing of multi-word expressions, and apophthegm anaphora, which allows the resolution of anaphoras in the source text. Recursive structural transfer. Given the range of possible syntactic structures, it is common for any two languages to have significantly different word orders. For example, in Welsh, verbs tend to be at the beginning of a sentence. In English, they tend to be in the middle, and in I can't quite read this word, this language, they tend to be at the end. Okay. These differences are problematic for apophthegm's finite state chunking module, which matches fixed sequences of words that must be contagious. This limitation means it is fairly easy to write rules which perform operations such as changing the order of nouns and adjectives, since these are usually adjacent, but changing larger structures is much harder. Switching the order of the subject and the main verb, for instance, would generally require writing a rule for each sequence of words that can make up each of those parts. The English-Spanish pair has more than 30 chunking rules for handling noun phrases with different number of determiners and adjectives, and those rules don't attempt to deal with all the structures that may occur in noun phrases, such as relative clauses. To deal with the limitations of finite state chunking, the apophthegm recursive module was developed by Daniel as part of Google Summer of Code 2019 to apply structural transfer rules recursively using the context-free grammars. Okay, let's go over it again. To deal with the limitations of finite state chunking, the apophthegm recursive module was developed by Daniel as part of Google Summer of Code 2019 to apply structural transfer rules recursively using the context-free grammars (CFGs) and a generalized left-right-right reduce parser. This makes it possible to process nested structures such as relative clauses or prepositional phrases within prepositional phrases. An example of the latter is shown in Figure 3 and 4 with the relevant rules in Figure 2. In this example, the word order of a set of nested prepositional phrases needs to be completely reversed. Or in linguistics, terms, the order of noun phrases and adpositional phrases each need to be reversed. Regardless the number of prepositional phrases involved in order to translate from English to Basque, a recursive approach to transfer can be helpful for translation pairs between syntactically more similar language as well. For example, in case of the English-Spanish noun phrase rules mentioned above, the more than 30 rules required for handling determinants, adjectives, and nouns can be simplified to less than 10 rules in apophthegm recursive, because more complicated structures can be handled by composing the simpler ones. In fact, the majority of these can be covered by using 3 rules, saying that a noun phrase is composed of a noun or an adjective and a noun phrase, or a determiner and a noun phrase. The 3 rules can immediately handle any number dyslexia.